this course. I would like maybe take this opportunity to thank the organizers for giving me the opportunity to do this lecture course. It's been really joyful. So today I will, well, let's summarize what we did. We proved these recursive formulae. And then what did we do with them? So we looked at some set BR of our set of interest. And we started with some blank upper bound on the probability of PAV, that this is on that whole set, like a big O of D over N. And then we ran through all of these one after the other. I don't know, not in that order, in some other order. And then what we got is that if you like move down to BR minus 4 of dm, on this set you get like the ratio RAB of D to be D over A, dA over dB times 1 plus big O of D over N. Okay, and then we move down once more. We applied the whole set of recursive relations once more. So we went down to some smaller subset, which was B R minus 8 of dm. And we got RAB to be equal to dA over dB times something more precise, something plus big O of D squared over N squared. Right? And then, okay, so now you can imagine, so if I just start further out, I can just do the same thing again. Like get closer and closer and actually get a really good approximation for RAB on dm or on B1 of dm. Okay, now what's the problem with this? So we did 2 iterations of these, and like the second was already a bit fiddly. The third iteration you can still do on paper. The fourth one, I think, is going to be hard. So the problem is that these formulae become unfeasible, unfeasible to calculate on paper. And there is another issue. Even if we were able to get some approximation, right? So after k iterations, what would be the precision? The precision would be like 1 plus big O of D over N to the k. And we want this precision to be little o, so we need for our argument that this D over N to the k is little o of 1 over N root D log N, or whatever degree deviation you have on your set dm. And so what you couldn't get with this with big O of 1 iterations, you could get you could get a formula for D up to, like, say, some n to the 1 minus epsilon, for epsilon greater than 0 being a constant. In theory, you can get up to that point, but the calculations will be horrible. So what do you do? So how do you go beyond? Well, I already hinted that these are sort of have a contractive behavior. And so let's make this precise. So what we will do is we will turn these formulae into operators. Let's start with this one. So instead of writing y a v b, we make this an operator y of a v b o of sets of functions, like a p and a y. And then that should whatever these 2 sets of functions are, it should give me a y again. So that gets inputs as a, v, b, and some sequence d. And then I just replace this PAV as like whatever function I have, p of a, v, D. This one I replace by a P. Let me write this as a V of that sequence. And this one I replace by my Y, which is my input here, A, V, B of this sequence. And here I also replace a P my bold P, which is my input of this operator. Okay, and I do this for all of them. So this I now call my probability operator that has as input an R and a P, and an A, V, and a D. This becomes my little R, and this becomes my little P. Okay. And yeah, let me just do that for all of them. So this becomes my bad operator of, as input, I need a probability-like function and a path probability-like function of A, B, D, little p, little y. And then finally, this becomes my ratio operator of, well, a bad, and bad has p and y's. P and y's of A, B, and D. Okay, and this is just now the bad of py. Okay, so is it clear what we are doing? We're just like taking our recursive relations and turn them into operators. Now, and P, Y, and R, I mean, so P is like a function, is a set of functions, right? That gives me something depending, I need to give it two distinct indices, A and B from N, and some degree sequence. But it's like an abstract function. I don't even have to require that this D is even or sums to something. It's just some set of functions. And similarly for Y and R. Now, these recursive relations that we have proved before, what do they say? So these they say, observation, that if I plug in there the real probability and the real ratio from GNM, then those are fixed points in quotes of these operators. So the real P, Y, and R are fixed points in the following sense. The real R is what I get if I apply this operator to my real probability and my real edge probability and real path probability. My probability is if I apply the probability operator to my real ratio and my real P, and my real Y is the Y of P and Y, right? In that sense, they are fixed points. And so if you think about operators and fixed points, like, so what we are talking about, this is a space of functions, or, yeah, space of, like, or pairs of functions, or triples of functions. And so I have here, let's say, a P, Y, and R. And so this set of operators move me somewhere else. That's like, well, let's say, that's like a C of P, Y, R. And the point is that somewhere there is my fixed point, which is my real P, my real Y, and my real R. And what I would like to say is that these operators are sort of contractive in some sense, which means that if I start not too far from PYR, and then this operator, if I apply this several times, should get me closer and closer to this fixed point, right? So we went through these calculations to get a feeling for this contraction, but that's exactly what's going on here. Okay, sorry, is there a question? No. So let's make precise what I mean by contraction. So of course, I mean, these are just functions of functions or operators. And I could put in here arbitrary stuff, and I would not have anything. Like I could put in like constants 1/2, and I would never see anything contracting to anywhere. So let me call a tuple Py. Oh, that's a definition. Call a tuple Py mu probability like if, or on some set, some d0, some set of sequences and indices, if the first assumption that you would like to make is that the probability, I mean the P function looks like a probability that is upper bounded by my mu, my density. So it's at most 0, at least 0, PAV of D, and that is at most mu for all D and D naught. Let's say AB, and N. Okay, so it looks like a probability upper bounded by some mu. B, I would like to relate this Y to P somehow. Okay, so there's this sum over all V not equal to AB of the P, Y AVBs of D is at most mu times dA for all D and D naught and AB and N. And the final one is distinct doesn't matter. And the final one is that 0 is at most YAVB of D is at most mu times the probability, like the PBV of D for all D and D naught, and D naught and A, B, B, and N. Assume that they are distinct if you need to. So that's what we call probability-like. And then it's not hard to show that if you look at the real probability, P and Y, they are, that pair of functions is mu probability-like. On the even, so well, let me write that out. B, so some ball of, let's write this out in the way we need it, 16 times log n of our dm. And, well, these are really only defined for even D. So let me say here all even D only, where where mu is 5 times, let's say, the m over n choose 2. And what you need to assume for this is something like that n log n cubed, say, is at most m is little o of n squared. Okay? I mean, you could here assume like a small constant times n squared. But what you want to say is that like the path probability is at most a factor of mu times your edge probability, one of the two edge probabilities. So that's not too hard to show. That's an exercise. And all that you need for this is the simple switching that we saw and the recursive relation for y. So those two are the only ingredients, and you can show that the real probability and the real two-edge path probability, they satisfy this definition. And with this that definition is exactly to claim that these are sort of contractive. So let me be precise what I mean by that. Okay. So this is the contraction lemma. What we need to assume is that we have two pairs of functions, so py and a p prime y prime. And you should think of this as this being the pair of real probabilities and this being a pair of approximations for them. So you want that they are both mu probability-like and on some, let me write a B2 of dm, or d0 actually, we don't even need to say anything. And r and r prime are just some functions. And psi is something greater than 0. So if you have that, then for A, you assume that if P is equal to 1 plus minus psi times P prime everywhere where you're talking about it, and you have that the Y prime is an approximation for Y, so Y is equal 1 plus minus psi times Y prime, then like this is for all sequences in B2 of d0. And for all AB, wherever I'm using this, I have uniformly that this P is between 1 plus psi times P prime with the same parameters and Y minus psi prime with the same parameters. So then if I apply the ratio operator to P and Y, then what I get is the ratio operator of P prime, Y prime times, now I get something better out, big O of mu times psi. Okay, I will write out all of these. I will argue for why one of these should be true and the other one is an exercise. But let me, this is on d0, say, and similar things you prove for the other two, for the probability and the Y operator. So the second one is if you have P is equal to 1 plus minus psi P prime on B2 of D, and you have an approximation for the ratios as well, R prime times 1 plus minus, here you assume the extra factor mu, then if you apply the probability operator, P of PR, this is the same as if you put in the two approximations times 1 plus big O of mu psi. Okay, and for space reasons, so yeah, let me just write the under some assumptions on, well, I'll squeeze it. So P is equal to P prime times 1 plus minus psi oh no, mu times psi. And y is equal to 1 plus minus psi times y prime. Then if you apply the operator, you get a factor of mu here as well for the approximation. So you get that y of py is equal to y of p prime, y prime times 1 plus big O of mu times psi. Okay, let me show you this one just so that it's not just like symbols flowing over your head. But it's not too hard to see this from there. Okay, now I'm missing one board space. Okay, just for B, so e.g. for B, so we have the operator, the probability operator of some probability-like function p and some y. So what is that? Let's just write it out here. So that is equal to the dv times the sum of the r, some r ba of d minus ev, 1 minus some p bv of some sequence d minus eb minus eb over 1 minus p av of d minus ea minus ev. Sorry? Oh, yeah. Oh, so thanks. Yes, P comes with an R and a P. Thank you. And so that's just the definition of the operator. Now I'm using, for B, I'm allowed to use that my P is psi close to P prime, and that my R is mu psi close to R prime. So I'm just replacing the R's and the P's by R primes and P primes, and I add the arrow. So this is equal to dv times the sum the R prime times 1 plus minus mu psi. And then here I have a 1 minus P times 1 plus minus psi over a P prime, and 1 minus a P prime times 1 plus minus xi. Okay, and now I'm using that this P prime is a mu probability-like function. So I'm using that this P prime has size at most mu. Okay, so I can write this as a dv times the sum and R prime. This one just becomes a 1 plus big O of mu times psi. And this one here becomes a 1 minus P prime plus big O of mu psi over the same thing. So I'm using an upper bound on the probability of mu to pull out this, to say, in this form here, this is an additive error of mu, or big O of mu times psi. So in total, that is just also a relative error of 1 plus big O of mu psi. Okay, so I'm starting with some approximation on the probability that is just like a factor of psi away. I'm throwing this through my probability operator, and I get something that's better, closer by a factor of mu. And mu was this d over n. So that's what we've seen, like applying these operators, well, the recursive function, the calculation yesterday. Okay, so It's really just look at these, what do you need to say that you get a better error out, and that is exactly what these conditions say. Okay, so, okay, so once you have the contraction lemma, then then I can now delete all of this. I think I keep that. And I think I can delete, yeah, I'll just delete this middle board for now. Okay. Good. So I already said the idea is that one of these two Py is your real probability together with your real your pair of actual probabilities. And now what should be an approximation? So if you look at this, then like you feel that there's something algorithmic about this. Do it again, do it again, do it again. And that's what we actually did. We put this in Maple, and we ran a couple of iterations with Maple. And then you get like you get more and more terms in your formulae for ratios and probabilities. And then you just guess a closed form. So here is our educated guess for something that should look like, that should be a good approximation for the formulae for real probabilities, real ratios, and real y's. Okay, so PAV guess of D is equal to, these are definitions, dA times dV. Well, we saw here a dN before, and the trick is that you write a dN minus 1, and that cancels a lot of your terms in the expansion, times 1 minus dA minus D, dB minus D over D, n minus 1 minus D. You have a ratio approximation, a guess for the ratio, which is, well, dA over dB, n minus dB over n minus dA. This we already saw as the fraction of the two binomials, probabilities in the binomial model. And then the term that you get here is dA minus dB over d squared n squared, the sum of the di minus d squared. So this was sort of the second moment term. And the y probability is just the guessed one, sorry, is what you guess for the path probability times what you guess for the edge probability, what you guess for the other edge in the slightly twisted sequence, EA minus EV. And then it turns out that this is already a really good approximation, and you only need to add 1 plus 1 on n. So these are our guesses for closed formulas of like what like a fixed point should look like. So another exercise is to show that these are also mu probability-like, with the same conditions. So on B 16 log n and conditions on M. Like the same as before, but this is now easy because these are explicit formulae. Like that is really easy to see or to do. And so what we have to do, there are two things we have to do. One, well, the most important thing is we have to run these once through our operators. and show that they are close to fixed points. So let me, I'm not going to do that calculation. That's like a longer one. But let me write the lemma. So the crucial lemma here is that these guessed formulae are close to a fixed point. Close to a fixed point, So under conditions, let me not write the conditions, if I plug in these guessed formulae into my operators, so P guessed and Y guessed, then I get the guessed ratio up to some error, like I don't get exactly the same. But this error is tiny. So here, this eta, you should just think of something super tiny. It's 1 over dn plus root d log n over n squared. So the exact form doesn't matter. It matters that this is super tiny. Okay? And then you get a similar thing for the others. So the y, or p, of r guessed and p guessed is just the p guessed. I'm writing here the same arrow, which is like a lie, but it's also just something tiny. And the final one is that if I apply the y to these guessed formulae, then I get just the guessed y out of it. Okay? And the proof of this is a calculation which, and I should say which doesn't fit anymore. So you don't get this everywhere. But you get, you have to assume something on where these approximations hold. So you get this on B 16 times log n of a dm star. So it's not exactly the dm we saw, but so dm star is the set of all d in dm, where you also assume that this di minus d squared is at most, say, a 2 times d times n. Okay, so the difference here is in dm, we had that the di's minus d is at most some root d log n. And then this one says, well, if you sum all of them, you can't have the deviation log n everywhere. In the sum, you have at most like the log n factor is shaved off. So it's a bit smaller set than what we had initially. It still contains the d regular, and it still has measure 1. So what we did earlier in the course would still go through for this one. But with these restrictions, you can verify this lemma in a handwritten, like you can go through these calculations and verify for yourself that you get these sort of near fixed point, that these are very close to the fixed point. And conditions on m are n times log n to some constant c is at most m. And for this hand calculation, you need that this is little of n to the log n to the 3/4. So for these ones, you can do calculation by hand. And let me just remark that the whole conjecture was for a wider degree spread, like a d to the 1/2 plus epsilon, and you don't want to have anything like this, and you want to have m to be a small constant times n squared. And for that, and like the whole, the whole conjecture. Conjecture was that you get some approximation for sequences that are of this form, that this is at most d to the 1/2 plus epsilon for some fixed epsilon, so wider degree spread and larger density. So for this, you need more precise versions of these. So need more precise formulas. And the calculations, I don't think they are possible to check by hand. Like the terms that you get fill pages. So for this, we need, or we use like a Maple program, which tells you, yes, you can throw out, like which terms you can throw out and what it simplifies to. So for the full conjecture, we need Maple, but for just getting the number of deregular graphs for the whole gap range, wait, this was this is possible to check by hand. So I think that's all I will say about that lemma. Like, I will not expect you to do this as an exercise. Right, but why is this good, right? So we need to finish off our proof sketch. And how much time do I have? Yeah, so let me do that one really quick and just adhere to your intuition. So you have your set of pairs of functions, py, that are all mu probability-like. Somewhere here you have your fixed point, which is the real probability, and your real y. And somewhere else you have your guessed formula, p guessed and y guessed. And then you say, well, this one, if I apply my operator, and now I should say there's actually only one operator. The operator is C on P, Y. And this is just formalizing doing all of this, like doing all of the recursions. So I want to get a pair again out of this. So I'm using my probability operator on, and I put everything away. So on my R of Py, so I'm applying my operator R to Py, and I use this as my first argument in P, and my second argument is just my P. And my second argument, what I get out of this, should be a Y function, so that's a Y on just Py. Okay, so that's just formalizing, do one after the other. So that C takes you somewhere else, to some approximation. C of P, G, and YG. Well, on the one hand, and this one is always equal to C of Py, because it's a fixed point, right? And on the one hand, you say, well, this one, it stays close to where I started. And on the other hand, it gets me mu closer to the fixed point. So do this log n times, and that's like a theoretical argument. Like a log n times, it tells you, well, every time I'm getting a factor of mu closer, but I'm also staying eta close to this one. So the two actually must be really close. Okay, so that's like a standard argument. So yeah, let me not write it. So, okay, let's just repeat. So if I apply this operator to this form, this lemma here says I'm staying eta close to the point where I started with every time. And every time I apply this one, I'm staying here. But also, the C gets me closer and closer to the fixed point. That was this contraction lemma. Okay, so let me stop this type of proof here and not go into details, because I want to have a few minutes to say something about the very dense enumeration, which is, yeah.
How do you know there's not any other fake fixed points?
So there could be another fixed point somewhere else, But you have to start with that the P guessed, Y guessed is the Py times 1 plus minus xi. And xi, you start with xi to be bigger of 1, like just 1, actually, right? Like any two probabilities, they have, show that both of these are bigger of dn, say, or something. And then you had the contraction lemma, which tells you, it really pulls you towards this fixed point. So you don't know what happens outside the space of mu probability-like functions. Who knows? But yeah, that was the contraction lemma. Yeah, any other questions? Good. Okay, that's all I will say about that method. So now I will say a few words about this completely different method when D is linear in N. Okay, so methods for D equals at least an N over log N. Okay. And this will just be a sketch, and so that you know what's going on. Okay. So let's start with a function f on n variables, which is equal to the product I equals 1 up to n, 1 plus xi xj. Oh, and I already did the first mistake. I'm taking the product over all pairs of distinct ij. So 1 less or equal than I, strictly less than j, less or equal than n. Just consider that function. Expand and write out like your set of monomials. Okay, so we have say a 1 plus x1, x2 times 1 plus x1, x3 times an x1 plus x2, x3 times 1 plus, let's say, x2, x10, I don't know. So what do I mean by expanding? How many monomials do I get when I expand? I have a choice between 1 and this product of xi's for every xi. So the number of monomials is equal to 2 to the n choose 2. Right? For every pair xi, xj, I have a choice to take 1 or this xi, xj. So what does one of these monomials correspond to? So let's say from this one I take x1, x2. From this one I take the 1. From this one I take x2, x3. And from this one I take, say, x2, x10. And I do this for every possible of these factors that comes up here. Well, that corresponds in a very natural way to a graph on n vertices, where for this one I decide to add the edge 1, 2. For this one I decide to not add the edge x1, x3. So let's say this is vertex 3. So I do not take that edge because I chose to take the 1. For this one I take x2, x3. So I'm adding the edge. And let's say here's your vertex 10. I also add that edge. And all others say I don't. So any one monomial corresponds in a natural way to a labeled graph on n vertices. Okay. Now if I see, expand and then collect all the terms that belong together. So, wait, before we do this, so this I can rewrite, right, as x1 to some alpha 1 times x2 to some alpha 2, and so on, xn up to some alpha n. What is this alpha 2? What does that correspond to? Yes, exactly. It's exactly the degree of 2 in this graph. Okay, so alpha 2 is the degree of vertex 2 in this graph G. Okay, so now you collect all of the terms together. So what that means is that the coefficient of x1 to the d, x2 to the d, up to xn to the d is the number of labeled graphs on n vertices where every vertex has degree d. Okay, that's a generating function approach. So that's step 1. Okay, and so all we have to do is to figure out what is this coefficient. And that's where we use Cauchy's formula. So this is a time to revise your complex analysis knowledge. Sorry? Okay. So what is Cauchy's formula? That if you have an f, this is in one variable for now. If you have a formula f from some neighborhood in C to C, and let me not say exactly what the definition is, but for us it's a polynomial. I mean, the real condition is that it's for every point in a neighborhood infinitely often differentiable, and for polynomials this is true. So for us, let's just stick to polynomials, and we are safe to apply this formula. Then U is an open neighborhood and 0 is contained in U for that. So then f of 0, you can write this as an integral in the complex numbers of f of z over z dz, where this is a closed curve around the origin living completely in U. Okay? So here's your 0. And then that theorem says that to evaluate your f of 0, all you have to do is take any curve around the origin, closed, and you walk around this once, then that value of f at 0 is exactly that, like, yeah, okay. And you can do this for the nth derivative as well. So that's n factorial over 2 pi I times this f of z over z to the n plus 1 dz. Okay, and then you need then you use that f for holomorphic, or you have a Taylor expansion. For polynomials, we have a Taylor expansion anyways. So then you use that. You can write f of x as f of 0 plus f prime at 0 times x plus, and then we get an f nth derivative at 0 over n factorial times x to the n. Okay, that's Taylor expansion in one variable. And all you realize is that this thing comes up here. Okay, and it tells you that plug this in here, and it gives you the coefficient of x to the n. Okay, and now you do this whole thing in many variables, and this is what you get. So the multivariate version is as follows, that this g of nd, which is the coefficient of x1 to the d to xn to the d of this product over all ij. Let me not use ij because I'm having I in the formula as a complex number. J not equal to k. And we take the product of 1 plus xj xk. And then by Cauchy formula magic, this is equal to 1 over 2 pi I to the n. And then you take an iterated integral of closed curves around the origin of the following. The product over all j not equal to k, 1 plus zj zk over z1 to the d plus 1 up to zn to the d plus 1, dz1 up to dzn. Okay, and then because f is a polynomial and defined everywhere, you can choose whichever one you want, whichever curve you want to go around. Like this curve can be anything. And what Brendan McKay and Nick Wormald did, they chose these curves to be circles around the origin of radius r, which is the square root of mu times 1 minus mu. That's the same mu, the density, as before. That's it. And then if you do that reparameterization, you get that this is equal to 1 over 2 pi r to the d to the n times an iterated integral from minus pi to pi. And then this product over all j less than k, 1 plus r squared e to the I theta j plus theta k over e to the I times d, and the sum of all the angles. Okay, d theta 1, d theta n. Okay, good. Now that looks like a horrible integral. So let me spend 2 more words on what's the overall approach, how you would attack this. Here, no, it's a D, because, yes, when you do change of variables, you have to remove this, and yeah, okay, good. Okay. Okay, and how would you attack anything like that? So for that, why do you choose circles of this radius? So these are functions that are defined on, I guess, c to the n. And on that area, you try to guess where this function has a high point. And then you try to show that your integral is, your measure, like your mass is concentrated around this high point. Let me tell you what I mean by this in one variable. So suppose you want to estimate some integral of some function f, or different f, so let's say h of t dt. And that h of t is of the form e to some other function g of t dt. Okay, then what this may or may not look like is something like let's just say it's like a normal distribution. Say g of t is equal to, what was my example? Minus t squared plus 2t. Then somewhere this has a high point. And what you're doing is that you show somehow that all that matters for that integral, most of this mass comes from nearby your high point. So you have to show that all the mass that you get from here is negligible. And then in order to evaluate that, you use so for that range, you use a quadratic approximation. So you just write that in your first two, three terms of your Taylor expansions. It's a polynomial, you can do integrals, and that's what you get. And then you get a formula out of all, and yeah, well, for this one it's much more complicated, but that's essentially the idea. You find a saddle point, you show that around that saddle point, all of that is, like, that's a high point. Everything which is far away, the total mass of that is negligible, and then you do quadratic approximation for that. Roughly, that's the idea. And then you get a formula, and which looks completely different than everything we have seen, but it's equivalent to the conjectured formula. Okay, so let me stop here. Yeah, oh, sorry, there was a question. Sorry.
The bound n is just to be negligible.
So,
because this is for high n.
Yeah, so this is for very high n, and if you have a function which looks like that, let's say you have here a factor n, then like this really shoots up, and everything else is, yeah. Thanks. Okay, any other question? Okay, then that's it.